Okay, perfect. So thank you everyone for joining in today's quick lecture. This topic is very close to my heart because I have worked very extensively with the progressive cavity pumping system. So I'm happy to introduce this very intricate topic to you guys, and let's see if we can learn something today. So progressive cavity pumping system, the agenda is that I want to share with you guys what is a progressive cavity pump, what are the different components of this progressive cavity pumps, all the way from the downhole components like pumps and the surface components like drive systems and auxiliary components like a variable speed drive or a variable frequency drive. In section 2, we are going to talk about the advantages of using a PCP system and what are the different application constraints, followed by a section on PCP versus the other artificial lift methods like gas lift systems and ESPs. And finally, we're going to talk about what is the natural constraint of a PCP system and how new technologies are overcoming that natural constraint. All right, so before we dive into what is a progressive cavity pump, we need to understand what is artificial lift, because artificial lift is one of the primary needs of an oil and gas well. It can be a water well as well, or a geothermal well. And artificial lift is a need across the board. So why artificial lift is required? Sometimes you have a well bore, for example, you drill a well and the reservoir pressure is high enough so that it can push the fluid all the way to the surface. This is what we call a natural lift. In this case, what you can see is there is a well bore, there's a high pressure reservoir, and you lower your tubing and you have your perforations at the very bottom, right over here. And what actually happens is that you will have enough wellbore fluid pressure that your differential pressure is going to push the fluid all the way from the reservoir to the surface. So you can see the oil going all the way to the surface wellhead. This is what we call natural lift. Sometimes you have a well bore and you have a low pressure reservoir right over here at the bottom. And what happens is that you will lower your tubing, you will have your perforation, but your reservoir pressure or the delta P differential pressure is not enough to push the fluid all the way to the surface. So you can see it stops somewhere halfway of the well bore fluid. So in that kind of a scenario, when you do not have enough reservoir pressure to push it all the way to the surface, you require something which is called an artificial lift system. Now, artificial lift systems are different type of systems that you select based on your well conditions and some other factors that we are going to talk about later on, which will help your wellbore fluid to come to the surface with some assistance. Now, there are different type of artificial lift systems. I'm going to start with the gas lift. We have progressive cavity pumps that we are going to discuss today. We have hydraulic pumps, and we have beam pumps. This is the most common type of artificial lift system that you guys are familiar of. Wherever we talk about oil and gas, you will always see pictures with the beam pump on the top. It's one of the most common type of artificial lift system out there. And last but not the least, it is electrical submersible pumps. Very high performance, it can result in a very high flow rates. Now, the natural question is, how do you select which method is appropriate for you? Now, what you see on the screen is just a generic comparison between different artificial lift systems, but it will give you an idea that what system is good for what. For example, when we talk about reciprocating rod lift, that means the pump jack that you saw in the earlier pictures, it is really good for gas. It's really good for corrosion handling. The operating volume is all the way from 20 barrels of fluid per day to 5,000 barrels of fluid per day. Temperatures from all the way to 290 degrees centigrade based on your metallurgy of the equipment that you select. But it's not really good for high solid handling. It's very fair for gas handling. And then for the offshore applications, it's a very poor application because it takes a lot of space. And offshore, we have a very space limitation. But if you go towards the progressive cavity pumps, they are really good for gas handling. They are really good for solids. They are, in fact, considered one of the excellent methods to, to, to select if there is a lot of solids in your wellbore. And they can go all the way to 5 barrels of fluid per day to 4,500 barrels of fluid per day. But their operating temperature is less. They can operate all the way to 120 degrees centigrade only. So if you have a high temperature downhole, it's very appropriate. So move on to the next one, which is gas lift. It's good all the way to 200 degrees centigrade because there are some elastomers that are used in the gas lift application. So those elastomers are only good for 200 degrees centigrade. But it is also good for the solids handling. It can also handle light oil. But in case of the progressive cavity pumps, they cannot handle light oil. And they are excellent for the offshore application. Now, these were some of the gas lift methods, some of the artificial lift methods. But let's say once you consider these with the electrical submersible pumps, they can go all the way to 30,000 barrels of fluid per day. So they are really good if you have to move a lot of fluid. They can go all the way to 200 degrees Celsius as well. Although they are good for corrosion handling, they are really bad for gas handling. So you have a lot of gas in the well. That means your GOR ratio is very high. It's not very good for that. And then they are not very good for the solid handling as well. So they're good for light oil. They are good for less gassy application, less solid application. But they are really good for excellent, in fact, for the offshore applications because they do not take a lot of space. Right? So different artificial lift methods have different selectivity, different criteria, different advantages and disadvantages. So you have to really dive into your wellbore fluid data. So when you do your well testing, you get your GOR, that is your gas to oil ratio, your water cut, that means how much water you have in the fluid, and what kind of injection you are doing. Is it very explosive fluid? Do you have H2S? What kind of a temperature are you getting? And then you select your artificial lift method based on all those constraints. Then similarly for your, in terms of your barrels of fluid per day versus the foot, the lifting, that lift that is required. So you can see that the rod pumps are good for 2,000 barrels of fluid per day, and the lift can go all the way to 7,000 feet. But when you go to the PC pumps, they as soon as you start increasing your barrels of fluid per day, your lift will decrease. And then similarly for your submersible pumps, they have a very wide operating range. You can see they cover all the way to from 50,000 barrels of fluid per day, and the lift can be high as well. Especially when you go towards like 5,000 barrels of fluid a day, you can set your pump really deep. But as you go towards the very high flow rates, like 50,000 barrels per day, it really limits the pump setting depth because you won't be able to get the lift that you need. And then your gas lift. Gas lift is really versatile mode of artificial lift system because you can see you can get a very high flow rate and you can set your guided gas lift systems at a very high depth. So you can get the lift that you want along with the fluid flow rate that you want as well. So this is just to stack up all these artificial lift systems with each other. If I have to pick one artificial lift method, which is very versatile and is going to be gas lift system, followed by submersible pumps, followed by hydraulic lift, followed by the PC pumps and the full rod. So PC pumps have their niche, they have their specific market that they are very preferred on. Specifically, they are considered one of the best methods to handle solid, and they are considered one of the best methods of artificial lift if you have very highly viscous fluid. That means very high API oil. Your PC pumps are considered one of the best methods. So let's talk about what the progressive cavity pumps are. Progressive cavity pumps were actually invented in 1932 by René Monod. He founded a company which is called PCM. This company is still around. They were the founders of the PCP for the oil and gas application. They still do it until this day, but they have also diversified into different industries. So in 79, the first PCPs were actually installed in sand producing heavy oil wells for Canada. Canada is considered one of the biggest markets of progressive cavity pumps, followed by Venezuela and Russia and other heavy oil producers like Oman and Middle East. It's a very simple system. It is essentially considered made up of two main downhole components. The first one is called a rotor. A rotor is just a helix that is rotating inside a stator. Stator is made up of two pieces. These are called stator housing, which you can see right over here. Stator is made up of a metal tube, and inside the metal tube there is an elastomer, which you can see right over here in black. Right. So the rotor actually rotates inside this stator, and the stator is made up of elastomer, and outside of the stator is made up of a metal tube. This metal tube is bonded with the elastomer by a special adhesive to make sure that it can handle the temperature up to 120 degrees Celsius. So the stator is run into the well at the bottom of the production tubing, so it is part of your completion. And then the rotor is actually connected with a series of rods called sucker rods, and then it is lowered. So your stator is deployed first. When your stator is at your pump setting depth, then you will lower your rotor all the way from the surface as a part of a rod string, and it goes at the bottom, and it is installed inside the stator. So the rotor will turn eccentrically in the stator, forming cavities from the intake. So usually at the bottom of your stator is what we call the intake, and at the top of the stator is what we call a discharge. Elastomer forms a very important part of your PCP. It determines the longevity and the reliability of your PCP. So the elastomer selection is usually considered very crucial, and a lot of experimentation and lab tests are done prior to selecting an elastomer for a particular field, because a particular field will have different field properties. We have four main types of elastomers. The composition of these elastomers varies from supplier to supplier, but essentially there is a high nitrile hard, high nitrile soft, fluorocarbon hard, and hydrogenated high nitrile hard, which is HHNH. Commonly used elastomers is high nitrile hard, followed by high nitrile soft. Elastomer compatibility tests, as I mentioned earlier, are required to measure the effect of the wellbore fluid on the material. These elastomer tests are usually run over a couple of days to see the swell of the elastomer, because what will happen is that the elastomer will swell as soon as it will come in contact with the wellbore fluid. So we want to determine how that swell looks like and what is the amount of swell, because the higher the swell is, the higher your torque is going to be, and we don't want that. Right? We want a sweet balance between the torque and the swell. Talking a little bit more about the progressive cavity pumps, the stator is essentially, as I mentioned earlier, you can see the cross section right over here. This is your steel tube. This is your elastomer in the black, and this elastomer, the interface of this elastomer and the steel is usually, there is either a chemical bonding or a mechanical bonding using adhesive. Right? So the rotor is actually made up of carbon steel, and then it is coated in a special type of coating. It can be either a chrome coated or a special type of nickel alloy coating. Right? So different type of pump models you can see right over here. They go all the way from 2.5-inch tubing to 3.5-inch tubing, suitable for 3.5-inch tubing and 4-inch tubing. You can see different geometries of the rotors, because the different geometries correspond to the different type of fluid rates, different type of solid handling, different type of some are good for the medium API oil, some are good for the heavy API oil. So you select your geometry based on that. Now let's talk about the complete like the progressive cavity pump system, all the way from downhole to the surface. On the surface, you have a surface drive head. We're going to talk a little bit more about the drive head in the coming slides. This drive head is either hydraulically operated or electrically operated using an electric motor. This electric motor is given power through what we call a power unit. If you don't have a power available on the site, if you have power available on the site, you can actually eliminate this power unit, and the power from the power unit or from the grid will actually go into the electric motor and into the variable frequency drive. This variable frequency drive protects the motor, and also it helps to make sure that you can control the speed of your progressive gravity pump. So drive head will convert the electrical energy to mechanical energy. So electrical motor will turn either a set of gears, either a set of pulleys through belts, and it will transmit the electrical power to mechanical power from the surface all the way to downhole. And as I mentioned earlier, that the rotor is connected with a series of rods called sucker rods all the way to the surface. The sucker rod will transmit power to the rotor. The rotor will rotate inside the stator. And at the very bottom, we have something which is called tag bar and an anchor. The anchor is to make sure that your complete string is actually anchored at the bottom, and it will not move or it will not rotate. Let's talk about power unit. Power unit is essentially it's like a genset or a hydraulic motor, which will provide electrical power or hydraulic power. It can be enclosed or it can be in a shack. And you have different kinds of fuel choices. You can have a propane. You can use the wellhead gas with the use of a scrubber, and it is a fully contained unit, which can be enclosed or not enclosed. Now, the next system is what we call a variable frequency drive. Variable frequency drive perform different functions. The first one is a soft start, so it makes sure that you can start your PCP at a very low RPM, and then you can actually start ramping your RPM. It regulates the speed. So if you set up a particular speed in your PCP system, it will regulate that speed. It will log all the data. So depending on the capability of a variable frequency drive, it can log the data. So it can log your temperature, it can log your RPM, your motor amps. That can store all that data if you have that capability. And then you can have a remote capabilities as well. So you can actually connect it with a radio, and it can transmit the data to a SCADA. And it also helps you to optimize your performance. So if you hook it up, or if you connect it with a gauge, a flow gauge, which can be a Venturi type of a gauge or impeller type of a flow meter. This flow meter can actually send data to your variable frequency drive. You can collect that data, you can optimize it. And in that way, you are always optimizing your well configuration. You can change your RPMs. You can pull your pump, push your pump. You can set it at a deeper depth, things like that. And then we have a surface drive head. We saw a picture of it. Now this is a more clearer picture. You have your motor, which is connected through, there is a pulley over here. Then a belt will transmit that to another pulley right over here. And then this pulley will drive what we call, there is a rod over here, which is called polish rod. This polish rod is actually connected with a series of sucker rod all the way to the rotor. Right? So the drive system actually consists of a prime mover, which is a motor. Your speed reduces with your belt and pulley system, and then your bearing housing, which is right over here. This is what we call a bearing housing. This bearing housing is to take the axial load of the string. So you see, right, your string is hanging, and all that load is actually there is thrust plates over here. There are thrust bearings right over here, which are taking all that weight off the rod string. Right? So it is not only transmitting power. The surface drive head is not only transmitting power, but it is also taking the load. And it will rotate the polish rod at the desired speed. So your rotor can actually rotate at that particular speed as well. It also provides the sealing around the polish rod. So ensures that the wellbore fluid will not have uncontained release, so it will provide that sealing right over here or right over here in another picture. Rod and the tubing strings. So rods are essentially sucker rods, which you can see right over here. They go all the way from the surface down to downhole, connected to your rotor. These sucker rods are connected with couplings. These sucker rods have one primary purpose, that is to transmit torque. That's it. Right? They are just there to transmit that torque from the surface to the downhole. So you can see that the selection of the rod string is usually done in a very appropriate manner, because a certain diameter of the rod string will only handle certain amount of load, which you can see right over here. The rod string size goes from all the way from 7/8 to 1 inch, 1 inch, inch and an eighth, and inch and a quarter, and different type of rod grades. And rod grade is essentially your metallurgy, and rod sizes and rod grades can handle all the way from 700 foot-pounds of torque to 2,500 foot-pounds of torque. So depending on your selection of your pump and how deep it is, you need to select your rods. The deeper you are setting your depth, the bigger your tubing is, and bigger your pump is, you will want to go with like inch and an eighth rod or 1 inch rod with a special alloy. Head at the flow rate. So let's talk about the main characteristics of the PCP. There are two main characteristics of the PCP when you will see the PCP nomenclature. The first one is your flow rate. So if the pump name is 60K1200, 60 is your flow rate, that is meter cubes per day, and then your 1200 is your head rating, so 1200 meters of water, right? So that is your head that this pump can provide. And this nomenclature is usually determined by ISO 15136, which is a ISO standard, which determines the nomenclature and the selection of the PCP. So it's not something which is unique to the supplier. It is determined by the ISO standard. Usually the suppliers will produce the PCP elements in a certain lift. For example, this is a 40K600. So this is a 600 meter lift pump. But if you want to get all the way to 2400 meter lift pump, all you have to do is stack up these elements, 4 of these elements together, weld them together, and you will get your lift that you want. So you reduce your stack up and you reduce your lift, you increase your stack up, you increase your lift. So the amount of elements you can stack up in series with each other will determine your lift. Displacement and head. So the PCB displacement, that is your cubes, that is your cubic meter per day, that is determined by a particular formula, which is 4 times of D by E by P. Now, what is D? D is the diameter of the rotor. E is the centricity of the rotor. So centricity is essentially how what is the distance from the center line of the rotor to the highest point or the crest of the rotor. And then pitch of the stator. Pitch of the stator is essentially your distance from one crest to another crest. So this will make one complete pitch of the stator. And you can see as this is a smaller pitch stator, a smaller pitch rotor. This is a medium pitch rotor, and this is a higher pitch rotor. So 2 times of your distance from your one crest to another crest is your pitch of the stator or pitch of the rotor. And the number of turns per day multiplied by, so number of turns per day is N, which is your RPM multiplied by 1440. So once you multiply all of these quantities together, you will determine your PCP. This is usually done at the time of developing the pump, and not at the time of selecting the pump, because once we have particular models available in each manufacturer's catalog, you pick up a pump based on the proven PCP displacement. So torque anchor is another of this. This goes at the very bottom of your PCP stator, and the torque anchor actually has two things. The one which I'm showing you over here, it can actually perform two functions. Number one, it is that it has slips. These slips have teeth. If you can imagine right over here, they have teeth. These teeth are made up of material which is really strong, so carburized steel. And what it does is that it prevents the rotation of the PCP in either direction. Right? Actually, in this case, this particular model of the PCP will prevent the rotation of the PCP in one direction, but it can rotate in the other direction. And that is very important because that can actually help to set or unset the anchor. So you rotate it in a particular direction, the slips will come out and they will anchor with the tubing. They will anchor inside the tubing. You can see right over here, figure 1. You can see the slips are fully retracted. And once you rotate it, there is a cam type of mechanism. This cam type of mechanism will push these slips towards the outward direction. Once it pushes to the outward direction, these slips will bite into the tubing and it will prevent any further rotation. So that is the purpose of the slips. The drag block at the bottom right over here, this helps to absorb the vibration because PCP can generate vibrations all the way to 20 Gs, 10 Gs, and in certain conditions, in case of very high swell and a lot of solid, it can generate vibrations up to 30 Gs as well. So a lot of vibration, right? So drag block is right over here. This acts like a vibration dampener. So it will absorb some of those vibrations. Advantages and constraints of the PCP system. Let's talk about the advantages first. Number one is that it is a very low capital intensive system, so you don't need to have a lot of money to deploy the system compared to the rest of the artificial lift methods like ESPs and rod pumps. Very high system efficiency, all the way 80% and above. In terms of wide range of application, they can be used for the medium oil. They can be used for the heavy oil. And then production can go all the way from 3 cubic meters of fluid per day all the way to 600. And they can be set at a very high depth. So all the way from 1200 meters of pump setting depth to 2600 meters of pump setting depth. And they can produce fluid with a very high cyanide concentration, high solids, high viscosity, and free gas up to 50%. They take a very less space. So this is a system comparison between a comparable PCP and a pump jack. So you can see to get the similar cubic meters of fluid per day, your PCP system is much, much smaller compared to a pump jack. So to get the same performance, you would need a pump jack which is this big of a size compared to PCP, which is really, really compact and small. So this is just a comparison between operating efficiency. The rod pumps have efficiency of 45% to 60%, considering whatever you will have energy losses on the prime mover, all the way from the surface to the downhole. PCP can go all the way to 40 to 70%. ESPs are usually 40 to 60% efficient with the induction motor. And then the gas lift is really, really inefficient, 5 to 30%. In terms of capital expenditure, so in terms of cost, PCPs are one of the cheapest methods of artificial lift, if I have to say, followed by sucker rod pump, followed by the ESP. Now, there are few limitations. The few limitations are, the first one is the temperature. You need to have temperature less than 120 degrees Celsius. If you have a temperature higher than that, you will have restrictions on the elastomer. You will not get the longevity and the reliability from the PCP. So you need to look into ESP. Then well bore and elastomer. So as I mentioned earlier, one of the things I've kept on repeating again and again, they are good for the medium API oil, that means medium viscosity, all the way to higher viscosity. They are not really good for the low viscosity oil. So light oil does not go very well with the PCP system. If you have a light oil with a high gas, your PCP is not the method you should select. You should go with the ESP or gas lift. So now naturally, that makes it limited in terms of application. Uh, when it makes it very limited in terms of application, this is one of the constraints of the PCP. And now I'm setting the stage for the next technology that I'm going to talk about that is the newest in the market, which is the PCP for the light oil. So industry has been working on the PCP for light oil for a very long time because they understand that it is the artificial lift method, which is very robust. It is very reliable. It is very cheap compared to sucker rod pumps and ESP. So why not develop an elastomer or a PCP, which is very good for the light oil applications. So that is what my next slide is going to talk about, PCP for the light oil application. But there are strict speed limitations as well. The maximum speed you can run your PCP is 500 RPM. Above this, either your rod strength will break, or you will have sealing issues, or either you will have reliability issues with your PCP elastomer. So these are some of the limitations of the PCP. Now, let's talk about the PCP for light oil application. Industry has been working it for quite some time. PCPs are not very ideal for the light oil application because of several technical and operational reasons. For example, the low viscosity challenge. PCPs rely on the fluid viscosity to maintain a seal between the rotor and stator, right? You remember that rotor that is rotating between the that is rotating in the stator. You require that fluid viscosity to maintain the seal lines between the rotor and the stator. Light oil have very low viscosity, so that can actually result in a higher slippage. That means you won't be able to seal. Reduce volumetric efficiency because if you higher slippages, that means your fluid is going from, it is slipping back into the previous cavity. That will reduce your volumetric efficiency and it will be very difficult to maintain pressure, right? Because your slippage is very high. Then similarly, when in the light oil applications, your wear and tear of the PCPs increases because higher viscosity oil, which is not present in case of a light oil, it is unable to lubricate properly. It will provide less lubricity. So, and the last is that usually light oil come with a high GOR, that is high gas to oil ratios, which can result in a gas locking and your elastomer degradation because you are just not getting enough fluid to cool that elastomer. And it is generating a lot of heat. That heat cannot be, it is finding it very difficult to dissipate that heat. And then last but not the least is thermal sensitivity. As I mentioned earlier, elastomer is a crucial part of the PCPs. So these elastomers are very sensitive to temperature. So higher temperature results in elastomer degradation. So if you are generating a lot of heat during this light oil application, that heat is not going to be dissipated. The elastomer will absorb that heat and start degrading. So these are some of the constraints on the PCP for why we do not use PCP for the light oil. So there is a new technology out in the market. This is called radar power edge. This is a special type of PCP that has been developed by one of the PCP providers, which gives operator more efficient reliability and reliable alternative to the rod lift system. And this can go all the way to 121 degrees centigrade as well. So there is a temperature limitation as well. But it is really good for the light oil API oils because now the elastomer has been selected in a way that it can dissipate that heat. Right? There is something else in this as well, which I'm not going to go deep into, but the stator design is very specific for the light oil application, which helps to reduce hysteresis. That is part of that failure mode. And then it is usually coupled with, rather than having a surface drive head system, it is coupled with what we call an ESPCP, which is electrical submersible progressive cavity pump. This combines the reliability and flexibility of the ESP technology with the PCP technology. So essentially you have your motor, downhole motor, permanent magnet motor at the very bottom, which is connected with the motor protector and a support unit to take the axial load as well as to provide the hydraulic compensation. And then you have your FSU, which is flex shaft unit, connected through a connection to your PCP. So your rotor and stator are right over here. and then you have your tubing connected with the PCP discharge. So the whole system, you do not have a surface drive head, you do not have sucker rod. So you have eliminated sucker rod, you have eliminated your surface drive head unit. That makes this whole system very reliable. Coupled with a permanent magnet motor, this is usually more energy efficient compared to an induction motor. So the whole system becomes really efficient, more than 80% of the efficiency. And then now you can deploy this system at a very good time. Right? So this is the latest and greatest in the PCP world, radar power edge, which is your special PCP, which is designed for the light oil. And this PCP can be connected to a downhole permanent magnet motor, which is highly efficient. This makes the whole system really efficient and really, really save on the CO2 emissions. So I think with this, this was a lot of information. I want to conclude this with a very concise slide on the PCP. So PCPs are really effective method, low flow artificial lift method for cost sensitive markets. They are primarily used onshore. That means land use only, but there are some applications for offshore uses as well. They are very superior in terms of solid handling, wax handling. However, temperature can be an enemy of a PCP. So we try to run them cool. We try not to go above the temperatures of 120 degrees Celsius, which is the limitation of your elastomer. We talked about how the temperature or the heat that is generated, if it's not dissipated very well, for example, in the light oil applications, your heat will start accumulating, it will start degrading the elastomer, you will have a stasis loss, and then it can result in early failure of the PCP. And we also talked about how conventional PCPs are usually compared to the conventional PCPs. ES PCPs can be set at a very high depth, so 3,000 meters and above. And then it is considered one of the best methods for the heavy oil and medium oil application with a very small footprint. However, with the advancements in the technology, now the PCP for the light oil market is not a dream anymore. It is very much a reality. And the reduced lift cost. So just because you have smaller upfront cost of the system, you have very small operating cost. This is overall the cost of fluid, cost of lifting the fluid all the way to the surface is considered very less compared to the rest of the artificial lift methods. All right. With this, I would like to conclude my presentation and we can open the forum for questions.
Thank you. Yes, as he said, if anyone has a question, please use the hand reaction or leave a comment in the chat. So we have a question from Ismail. Let's see what he has to say.
Oh, my goodness, what have I done? Hello? Hello?
Yes, Ismail, we can hear you.
Oh, I thought I closed something else. I never, I did not see my screen. All right, let me proceed. The question is this: what are the long-term environmental and operational limitations of choosing progressive cavity pumps over traditional artificial lift systems?
Ismail, sorry, I didn't catch the earlier part of your question. Can you repeat that?
Okay, I'm a little bit distracted. My child is distracting. That is why I read it that way. I'm sorry. Let me focus right now. Okay. What are the long-term environmental and operational implications of choosing progressive cavity pumps over traditional artificial lift systems?
All right. That's a very good question. So compared to other artificial lift methods, progressive cavity pumps, the first is the footprint, right? You saw that, I saw this slide where you were seeing a PCP with a pump jack. PCPs are really compact, right? So you can deploy them even if you have fields which are in the populated area. So people won't notice them compared to a pump jack, which is usually very visible from very far. So the environmental footprint is very less. Second thing is the noise footprint is also very less because it's an electric motor. and the moving components are really contained inside housing. So it's not very noisy. You would hardly be able to. I think at like 10 to 50 meters, the noise is around 50 to 70 decibels. So a really, really quiet system. So that is compared to a pump jack, compared to a gas lift system, which is require a on-site compressor. So it is loud. Pump jacks are also loud. They are not quiet. The noise pollution produced by the PCPs is really bad. Secondly, it's the CO2 emissions. The CO2 emissions from a PCP system are much less compared to other methods because it's very efficient. As I mentioned earlier, it's between 70 to 80% efficiency, right? So it's very efficient. So amount of energy that you require to run this PCP is really less, really, really less. With the advancements in technology, we rather than using induction motor, we are now using sometimes some of the locations, if they can, they use permanent magnet motors, which are usually more efficient compared to induction motor. So your CO2 emissions per barrel is also very less compared to rest of the metals. So
Thank you, sir. I'm grateful. Yes, sir.
Okay, we have another question from CC Jules.
Okay, thank you. A very good presentation. My question is, I have two questions. The first is, what do you stand by RPM? Because I got many definition, like revolution per minute, like reservoir performance monitor, but in oil gas context, what can be the RPM and what can be the flow count? Second question is the what you say the progressive cavity pump. Is there the same release or same version on any oil gas plant, like in USA, like in Middle East oil gas plant and so on? Are they the same, or there are many versions of the PCP?
Good question. So the first one, RPM, whenever I said RPM, that means revolutions per minute, so your rotation speed of your PCP. Regarding the versions so the main system will remain same, right? The concept will remain same, the main components will remain same. However, the pump length, pump geometry is based on your area. So the pump geometry that is used in US and the elastomer that is used in US, not even US, let's talk about particular field. So if you have one particular field in an area, if it is using elastomer and pumps for that field, you go to a next field and you may have to change your elastomer. The reason for that is between fields, your fluid properties will differ. Some fields have high H2S, some fields do not have H2S, some fields have high water cut, some of the fields have almost zero water cut. So with this, your pump selection will change. It's specific to a field, it's not specific to an area.
In the Middle East, like in Qatar, the Emirate, United, and so on, in the same version of PCP.
It can use same version, it cannot use same version. But overall, the system will remain same. You will have a top drive at the top. You will have a rod string. You will have a PCP. You will have a torque. This configuration does not change.
It is not depending on the environment of use of the plant.
No, it does not.
Using PCP. Okay. Okay, thank you.
Let's go with Olufemi.
Thank you very much. Can you hear me, please?
Yes, we can.
Okay, thank you, sir, Dr. Hassaan Ali. I'm sorry I joined a bit late. Please, my question is, what is the maximum pressure rating for operating the PCP pump? And secondly, how can we compare the use of PCP pump with in situ combustion or with water injection to enable us to produce the heavy oil? Thank you, sir.
All right, Olufemi, let's talk about your first questions first, and then I would want you to repeat your second question. The first question is about
Maximum.
Maximum pressure. Maximum pressure this PCPs can go to is around 36,000 kPa. That is the maximum which I have seen in the industry. That is the maximum it can produce. One thing to mention, I forgot to mention, is that this is a positive displacement pump. That means it will keep on producing pressure if there is a flow line restriction, right? If you close your flow line valve, it will keep on producing pressure until it bursts the flow line, or it will damage the pump. So, but if you want to talk about what is the maximum a PCP can produce, a PCP can produce all the way to 36,000 kPa.
Thank you, sir. Can you hear me?
Yeah, second question.
Yeah, the second question is how do we compare the PCP operation with water injection or in situ combustion to enable us to produce the heavy oil?
Water injection, I'm trying to piece your question together. So water injection and PCP are two different things. PCP is lifting the fluid all the way to the surface. Water injection is injecting the water into the reservoir, and that is usually done for two or three purposes. Water injection is either done because you have excess water that you cannot dispose of anyway, so you inject it back into the reservoir. The second way is what we call so usually you will have water injector around the field, and you will inject water around that field. And what will happen is, as you guys know, right, oil and water do not mix together. So the oil will come at the very top. So what will happen is that all these injectors around the field will push that oil from the very middle. So you have injectors around the field and then a producer at the middle of the field. And all that water is going to push that oil all the way through the producing. So if I don't know if I understood your questions correctly or not, but those are two different things.
What about the costs?
Cost of the system or the cost per barrel?
Yeah, cost of the operations.
The cost of the operation, usually compared to the other artificial lift methods, it is considered very, it's much cheaper to operate. I cannot give you a dollar number. The reason for that is it will vary from area to area. So the cost of operation in US is much more difficult. It's much more different from the cost of operation, let's say in Middle East, right? But the cost of lift per barrel is all the way from $3 per barrel to $8 per barrel.
Okay, thank you very much, sir.
Okay.
Okay, let's go with Emmanuel.
Emmanuel, do you have any question? You're on the mute.
Emmanuel, can you please unmute yourself? If not, we go with Ismail. Well, let's go with Ismail. If you have a question, Emmanuel, you can write it in the chat.
Hello. I don't know what happened to my Zoom today. Whenever I click, it shows another thing. Okay, let me proceed to the question. I have another question. The question is this, sir. What innovations could be introduced to overcome the limitations of gas handling in progressive cavity pumps?
Good question. All right. So not shown in this picture. As I mentioned earlier, the ESPCP systems have been around for quite some time, but this one is This is the one with the so this is the general configuration of the ES-PCP system. So one of the components that I didn't show in this one is what we called a pump intake, right? So at the pump intake, right over here, there can, if there is a high GOR ratio well, right, high gas to oil ratio, there is something which is called a variable gas separator, VGSA. Variable gas separator is a special type of downhole gas separator that can actually reduce the gas that is being ingested into the PCP. So what it will do is it has a special geometry, that geometry based on the viscosity of the fluid and the pressure of the fluid. It will push the gas out through the ports, and it will just push the fluid through the PCP. So that improves the gas handling of the PCP. It's not a very common technology as of now. This is considered premium, and there have been some deployments, but it's not very commonly found.
Thank you, sir. I'm grateful. Mm.
Do anyone else have a question? Let's try again with Emmanuel to unmute himself. Well, it seems we don't have any question. You want to say something before we go, Hassaan Ali?
Yes, thank you very much for being a very patient listeners, guys. I know this has been, I see a lot of common faces now. So I hope you enjoy the series of lectures on different artificial lift systems. Thank you for being very patient, and I really appreciated the questions. I hope to see you guys soon again.